This is the first of two videos dealing with the chain rule, and what the chain rule is designed to do is find derivatives of composite functions. So in our warm-up here, we have a 2x plus 1, that quantity being cubed, and we have to find its derivative. And up until now, the only way you know how to do it is to expand this binomial. So we're going to expand this thing out. What that means is we're going to have to consider 2x plus 1 as a factor 3 times. And then multiply two of them together first. And then multiply that result times our third binomial. And now that I have this written in this form, I'm ready to use the power rule to find the derivative. And that brings me to here. And I can see I have a common factor of 6, so I'm going to go ahead and factor that 6 out. And when I do that, that leaves me here. And then I spotted a perfect square trinomial that I factored into 2x plus 1 quantity squared. So my derivative is this guy down here. This is something algebraically you spend some time in Algebra 2 doing, but what we're going to do is find a simpler way to do that, because once I increase this power to like a 10, this becomes really cumbersome to do. So we're looking for a little shortcut. And you might already have some ideas as you look at what our original problem was and what our derivative is. You might start seeing some connections and some patterns happening. Before we go into the specifics of the chain rule, it's important to understand what a composite function is so that you know when to use the chain rule. So let's talk about when you're going to use it first, and then we'll talk about what it actually is. So there's some functions that do not require a chain rule, and this is where you've lived your life so far. So when I have y equals x cubed, I can do that derivative. It would just be 3x squared. Let's look at how the problem in the next column is a little bit different. And over here we're looking at functions that do need a chain rule to find the derivative because they are composite functions. So right here I just had x being cubed, but here I have 2x plus 1 being cubed. So I've actually got a function, 2x plus 1, being plugged into that cubing function, and this guy is going to need a chain rule. Going down to the next one. So here I have y equals sine x, and you know that that derivative is cosine x. And no chain rule was needed for that one. But look at how that's different from the one in the next column. So here I'm not doing the sine of just an x, I'm doing sine of 5x squared. So what I've got is something more complicated than just an x that I'm finding the sine of. So this one is going to need a chain rule. And in the next one down, I've got the square root of x, and you know how to do the square root of x derivative. I do my rewrite first, rewrite that radical as 1/2 power, and then I just apply my power rule. So bring down the power, subtract 1 from the power. So look at the difference between this square root of x, and then this one says the square root of something more complicated than x, namely 3x to the 4th minus 2. So over here, no chain rule needed. Over here, I am going to need a chain rule. And then my last one is y equals tangent x, and that is simply just an x, so you can find its derivative. And no chain rule was needed, but when I look at the next one, and this one, it'll help you see a little bit better if you do a little rewrite. So remember that when you have a 4th power on a trig function here, you can rewrite that with parentheses on the outside of the trig function. And that becomes tangent x to the 4th. And then you can see that in this one, I've got a tangent x being plugged into a 4th power function. So now that you see when you need to use it, so with this middle column, these all need a chain rule. The first column is just business as usual, what we've been doing for the past month. So once you've decided that you need a chain rule, you have to pick out the outer function and the inner function. So which function is on the outside and which function is on the inside. So on this first one, 2x plus 1 to the 3rd. So my inner function is that 2x plus 1, and I'm defining that as u. So over here, this whole inside function is u. And then y is taking that u and raising it to the 3rd power. So this is my inner function, and that cubing is my outer function. On my next one, I can see that that 5x squared is being plugged into the sign. So my inner function is the 5x squared, and I'm defining that as u. So my inner function here is u. So now my y equals sine of u, and that is my outer function. And on my next one, my inner function is going to be what's inside the square root. So my inner function is that 3x to the fourth minus 2. And you can see that my outer function y is square rooting that function which I'm calling u. So my outer function is the square root of u. And for my last one here, it really took rewriting this trig function to get a sense of which function was inner, which is the tangent, and which is outer, which is that fourth power. So all we've done so far is we've looked at a composite function, and we have just split it into an inner function and an outer function. So now let's look at what the chain rule says. So I'm going to give it to you in 3 different ways here. The first one is the Lagrange notation. So y equals f of g of x, so there's our composite function. And here's what the chain rule says. It says do f prime of g of x times g prime of x. Notice that what I've created right here is another composite function. So this doesn't say f prime times g of x, it's f prime of g of x, and that's an important distinction to make. And in words, it would say this: derivative of the outside function. So when I'm looking at this, f is my outside function, and g is my inside function. So I do derivative of the outside, that's this part. You leave the inside alone. So you just rewrite g of x just like it looks. So leave the inside alone is what's going on right here. And then you multiply times the derivative of the inside function, and that is the last little link in your chain right here. So derivative of the outside function, leave the inside function alone, times derivative of that inner function. And another notation, we're going to kind of dwell on this one today in the examples that we do. Again, you're given y equals f of g of x, your composite function, and you're splitting it up, and this is what we had done above. We split it up into your inner function and your outer function. So then if you want to find dy dx, that's the derivative of y with respect to our variable x, you're going to take your outer function, which is expressed as a function of u. And if you just look at one of these up here, that's what I was doing in that table above. And I do the derivative of y with respect to u. And then I multiply times the derivative of u with respect to x. Notice that was just how we defined our inner function, so you would just do that derivative. But look at what's happened if you look at this statement algebraically. What you would see is that these du's would cancel out, and I am just left with dy dx, and that is what I'm trying to find. Let's look at a few examples, and these are the ones that are in the table, and we've already taken the time to pull it apart. So we already know the inner and the outer functions for these 4 problems back here. So we're finding what the inner function is that 2x plus 1. So we define that as u, and then what y is doing is taking that u and cubing it. The next thing I'm going to do is find the derivative of each one of these equations with respect to the variable that's within that equation. And this is where understanding that Leibniz notation is really crucial. So the derivative of y with respect to u is just going to be at 3u squared. And the next statement wants the derivative of u with respect to x, and that is just going to be a 2. Just a reminder how we wrote that chain rule on the front right here. So dy dx, the derivative of y with respect to x, I just take these 2 derivatives, my dy du and my du dx, and I multiply them together. And then I can simplify this and call that 6u squared. And then the last thing I need to do is get this back to my original variable. If this says dy dx, that means the variable I should see in my answer is an x. So I go back to how I originally defined u, which is 2x plus 1, and I just substitute that 2x plus 1 back in for my u. And that gives me my answer, and you'll see that was the answer to the warm-up question when I took that 2x plus 1 and I actually cubed it out. Let's go on and do question 2. And again, I've already taken the time on the front to split this into inner and outer. So 5x squared is my inner function, and y is taking that and doing the sign of it. The next step was to do the derivative of each one of these equations with respect to their variable. Derivative of sine u is cosine u, and the derivative of 5x squared is 10x. My next move was to take these and multiply them together. And then if I'm looking for dy dx, that means that I need my equation here expressed in terms of x, so I have to go back and do something with that u. So I look back here at the beginning and I see that that u was originally defined as 5x squared, so I'm going to put that 5x squared back in. And that gives me my derivative here. So we'll just repeat this procedure for number 3. So again, my first step is to pull out the inner and the outer. So my u is the 3x to the 4th minus 2, and what y is doing is taking that u and raising it to the 1/2 power. That's the square root. The next thing I'm going to do is the derivative of each one of these equations with respect to the variable. So here are my derivatives, dy du, because that's a y and that's a u. I just do a power rule. And this one, I would do du dx because the function is called u. And within that function, I have my variable x. So du dx is 12x cubed. And once I do that, I multiply these two together. And there's a little bit of cleanup I can do here. So I've got the 1/2 of 12, would just turn that coefficient into a 6. And also this u to the negative 1/2, a negative exponent, is going to push it down below. And then my last move is to get this all in terms of x. So where I see that u, I'm going to go back over here to how I originally defined u and put that 3x to the 4th minus 2 in place of it. And I also took this back into square root notation when I did that. And my last one, this y equals tangent to the 4th power of x. Make sure when you have a trig function with a power on it, take the time to rewrite that power on the outside. And when it's written in this form, you really get a sense of that tangent x is your inside function and that 4th power is your outer function. So I identify my inner function as tangent x, my outer function is that tangent being raised to the 4th power. And then I do my derivatives. And once I have my derivatives, I just multiply those two together. And lastly, I just go back to my original variable. So when this says dy dx, I need to go back to my variable of x, so I can see I'm just going to replace that with the tangent x. And that gives me my final derivative answer. We're going to extend our chain rule in the next section to include other rules, and we're going to look at tables as well. But just make sure for right now you know when to use a chain rule. So you're looking for that composite function, that f of g of x format. You can identify your inner or your outer, just like we did here. And then you're just going to follow what we dwelled on today was this Leibniz notation of the derivative that was written right down here.